So maybe only half, well, let me ask, how many of you know what ray tracing is? Okay, 62%. That's pretty good. Ray tracing is the computer graphics algorithm that was used to draw this picture right here. So the question is, when will video games look like that? So to dive in, I wonder if this will work. Okay, Leo, looks like you're going to be pressing the button for me. I'll just say, go to the next slide. So, okay, wow. This is the next slide. Okay. Okay, am I just... Okay. So the remote control is by Logitech, though, not NVIDIA. So, okay, I'll just ask you to go to the next slide. Go ahead. So I wanted to you've pretty much all heard of NVIDIA before, but this is the chips we've made over time, each of our families of graphics accelerators. The company started in 1993. Our first successful product was the Riva 128 with 3 million transistors, and we have progressed over time. Our current family of processors, our current architecture is called Kepler. Our mid-range Kepler chip that you know as the GeForce GTX 680 has 3.5 billion transistors. So it's large in size. Our high-end, the K20, which will be coming out very soon, is many, many more transistors than that. Okay, next slide. Okay, this has nothing to do with ray tracing, but I'm excited about it. Just this week, NVIDIA is announcing this supercomputer, Titan. It's at the United States Department of Energy Oak Ridge National Labs. It's the largest supercomputer in the world. It's 20 petaflops. It's made of 18,833 NVIDIA Kepler processors. So the reason you can't buy our high-end Kepler processor yet is that they're all in this box. So if you can get into the National Lab, maybe you can pull one out. But I'm really excited about this, and National Geographic magazine just said, in a breakthrough that harnesses video game technology for solving science's most complex mysteries, we've made this machine. So this is video game technology in the extreme, so I'm pretty excited about this. Okay, next slide. Okay, did I do that? I think I did. Okay, Logitech comes through for us. Good. Okay, so on to drawing pictures. The way that NVIDIA chips have always drawn pictures is with a process called rasterization. This is what OpenGL and Direct3D do. For each triangle in the scene, project it onto the screen, find the pixels that the triangle touches, and then figure out what color they are. Ray tracing is an inverted algorithm from that. For each pixel on the screen, figure out what color it is. Do this by tracing a ray from the eye through the pixel out into the world and see what it hits. Get a set of all the things that it hits, find the one that's closest, and that's what you shape. That's what you compute the color. So, more generalized, ray tracing is a database operation. It's a query where, given this database, given this ray, tell me the closest hit, or tell me all of the hits, or give me any one of the hits. Those are the three database queries that ray tracing is. Okay, so ray tracing for graphics was invented in 1968 by Arthur Appel, and then again in 1980 by Turner Whitted, one of my old professors. And this was his picture. In 1984, next slide. I wonder if it's a battery problem. 1984, Rob Cook generalized this a little bit by tracing many arrays per pixel to integrate over domain. Leo, can you go to the next slide? Okay, this is okay. And then in 1986, Jim Kajia, who's now at Microsoft Research, realized that integrating over the domain of a pixel to get a soft shadow, or to get a glossy specular highlight, or to get motion blur, or to get depth of field, any of these isolated integrals where you sampled lots of rays and averaged them together to create the integral, you can generalize all those and make another leap forward in quality. And this is path tracing. The path tracing approach is to trace a ray from the eye through the pixel out into the world and bounce randomly and see what you hit. Do that maybe 100 times per pixel and integrate the resulting colors along all of those ray paths to give you the color for the pixel. And it's an average color across all of those ray paths. Next. Okay. So each of these three approaches, Quidden ray tracing, Cook distribution ray tracing, and Kajia's path tracing, are about an order of magnitude more complex than the last one. And so over time they're going to become interactive, and then they'll become truly real time, but they'll do it one after another. And I would say that right now we're about right here. So distribution ray tracing we can usually do in real time, and path tracing is sort of interactive and sort of still a batch process. So we want ray tracing, we want its quality relative to the OpenGL and Direct3D that we have today, but the problem is it's slow. So how do we optimize the ray tracing algorithm? So the same way we optimize anything, I will assert, there's three approaches. One is use the right processor, GPU. Two is improve your algorithm. And three is tune for the architecture, micro-optimizations. And, okay, there's some latency on this thing. So I'll summarize those as get better hardware, get better software, and get better middleware. So what my group does at NVIDIA is the better middleware. Optics is NVIDIA's ray tracing engine. Think of it like OpenGL or Direct3D, but with ray tracing. And it runs on all modern NVIDIA GPUs. So now let me give you one quick example of what optics does for you. What is better about our middleware? So one difficult problem in ray tracing is if you have a million triangles in your scene, in your game level, how do you not compare every ray against every triangle? If you've got even a small 2 million rays per frame times a million triangles, that's 2 trillion ray triangle intersections. You don't want to do that, trust me. So what you want to do instead is use a spatial data structure, the one that is most common and that my group has published several papers on, is the bounding value hierarchy. This one over on the left. So you imagine an axis-aligned bounding box around the entire world, around all the geometry. Then you partition the geometry into
next.
Okay, you partition the geometry into 2 halves, and then each of those into 2 halves, and so on, until each of these white boxes has only 1 or 2 or 3 triangles in it, instead of the million that you started with. And then you make a binary tree over those boxes. And then you, when you're tracing a ray, okay, that's not gonna work. When you're tracing a ray, you trace the ray against the box containing the whole world. And if it hits the box, then you compare the ray against the 2 child boxes and see if it hits those, and so on, until you get down to boxes that have triangles inside them instead of boxes, and then you compare the ray against just those 2 or 3 triangles. It's a lot faster. Okay, the slide, if we used a better laptop, this slide would say that we've shipped about 380 million GPUs that run optics. And by the way, that's more than all of the Wii's, PS3s, and Xbox 360s in the world, by far. Okay, so that's optics. You can download optics today. Now, I wonder if someone could get me an additional battery for this. Maybe. You can download optics today at developer.nvidia.com. It's free. It runs on Windows, Linux, and Mac. Now I'm going to talk about ray tracing in games specifically. So first, I talked a lot about how ray tracing is a complex problem and it's slow. And so the first uses of ray tracing for the purpose of games are not real time in the game itself. Okay, Leo, can you go to the next slide? Okay, so the first uses of ray tracing in games are for light making. Okay, this one right here. So there's at least 5 companies right now that are using optics for light making. Light making is the generic term for the offline pre-process of computing anything that your algorithm, that your game engine wants to do for lighting. And it involves computing values of vertices, computing values of texture maps, and then feeding those to the game engine so that the remaining pieces of the computation can be done in real time. So this company, Geomerics, specializes in lighting for games. So Geomerics technology is used in Unreal Engine 3, for example, and then it's also sold directly to several high-end game titles. So in this scene we have skylight, we have sunlight, we have point lights from these hanging lamps, we have radiosity, indirect lighting, and we have ambient occlusion. So there's a lot going on here, lighting-wise, and this is real time. Okay. Let's see. Well, okay. So how does Geomerics get all of that in real time? Part of the, it involves a big pre-process that includes ray tracing. The directional light from the sun and the point lights are all ray traced to compute the sharp shadows and the soft shadows, and then the ambient occlusion is pre-baked. And then the radiosity, and all of that's done directly using ray tracing. And then the radiosity is also computed using ray tracing with optics. So this is the standard radiosity matrix. How many of you recognize this matrix or know the radiosity algorithm? Okay, radiosity is kind of old. It's from the 80s, but it still has its place. So these F values are the form factors. They tell how much light goes from this triangle to this triangle. Okay, so for every pair of triangles in the world, light may bounce from one to the other, and you want to know how much. And that's what the F value is between those two triangles. And that's computed by tracing a whole bunch of rays between the two triangles and counting how many of them can see, how many of them arrive, versus how many hit something else along the way. That gives you F. So that's the offline pre-process, is make the matrix, then compress the matrix, then at runtime in the game engine, you just hand it one of these vectors that contains all of all of the light being emitted, and then you multiply the vector by the matrix, and that gives you the amount of indirect light bouncing off of each triangle. So that's a very fast process. Okay, next slide. Okay, back one. Okay, so this one. Okay, so this is all of the optics code that was required to do this. They just hand us the rays and say trace them, and then we hand them back a list of everything that they hit. And optics for this works on all NVIDIA GPUs and even on CPUs. Okay, next slide. Okay, we're also being used by SBGames, which makes EVE Online. We're being used in a variety of ways at EVE Online. Most are offline, but some are not. So their first goal is to make a portrait of the character. The player gets to put the tattoos, gets to choose the hair color, choose the outfit, choose the hairstyle, choose male versus female, the race, all these things. There's millions of possible characters, plus an infinity of different textures that you can have in the tattoos. So, so they want to make high-quality portraits of the characters. Here's two right here. So these are done on SBGames server farm after the player creates the character, and then once it's rendered with optics, the resulting still image avatar is broadcast to the player who owns that character and to all other characters interacting with it. Now, another thing they do here is the hair here is made of Bezier billboards. Okay, so these are mathematical curved surfaces that are being ray traced. It would look really, really bad in direct 3D, according to Bert, the guy at SBGames. So this is something that they're getting out of optics in their offline process. They're also using optics for offline and real-time rendering of ships. So if you're in the mode where you're not in combat with several ships, but you're just looking at your ship and you're configuring it and you're buying stuff for your ship, they will real-time ray trace that for you on their server and download to you that ray traced image. So you'll get this kind of quality when you're configuring your ship, and then when you go into battle and there's 10 ships on the screen, they go back to direct 3D quality. Also, CCP is experimenting with using this approach for cinematics. So they can pre-render everything using all the exact same assets that the D3D pipeline requires, but it's cinematic quality. And so they don't have to have a separate pipeline for cinematics. Okay, the final offline baking system that I'd like to talk about is one that's being used by Bungie. It's still in development. It's being developed by Peter Pike-Sloan of NVIDIA Research, who's in my office. He published a paper on it at ETSR a year ago. And, but we own this code, and if any of you want to use it for your light baking, just ask us. So this is baking the light into the vertices of the model, not into texels in a texture map. Why is this good? It's good for, it uses less memory, and it loads less memory than a texture, so it consumes less bandwidth. You don't have to have UV texture coordinates on your model if you don't want to. And this is good for low frequency effects. So let me give you an example of that. Next slide. Okay, so this is from Disney's Mickey game. So you see the low frequency lighting. This is just ambient occlusion. You can see that the triangles are very large, and the lighting is smoothly interpolated across each triangle. And this only works well if the level is not dynamic, if you're not destroying geometry and things like that. This is pre-baked, so it works on static geometry. Okay, so good luck translating this slide. Sorry about this. What we have here is the approach to do it. So this is a vertex right here. We're trying to compute the ambient occlusion value and any other lighting values that will be baked into that vertex. So what we do is we sample using ray tracing from all of these locations X. And we compute the ambient occlusion and all of the spherical harmonics and pre-computed gradients transfer at all of these X locations. And then using using this piecewise linear equation, but using a least squares fit of this equation to these values, we compute the value at the vertex. Okay, so by using least squares, we get much smoother lighting, and we also avoid problems in occluded areas. So if a triangle in this big model is only halfway visible and halfway invisible, we want the lighting of the vertices to only depend on what's visible. We don't want the invisible stuff to be pulling the values off in the wrong direction and causing artifacts. So this is a version that does not do least squares and has artifacts. You see all these high frequency junk right here and everywhere else. So using our approach, okay, next slide, it looks like this. So this is from another Mickey level in a shipping game. So, and this was done before optics was being used to do this. So this is CPU ray tracing, but now it can be done with optics much quicker. And so the way Bungie is going to use this is they're going to have a server farm that all their lighters will submit levels to, and it will bake them in half a minute to a minute, and then the lighter can visualize the level in just 1 minute. Okay, next slide. So all of that is offline light baking. Okay, this is supposed to be a video. Is there any, maybe you can get it to play, maybe not. So Lego is also using optics in Lego Universe. So in Lego Universe, people can take Legos online and build their own models, their own characters, their own ships, houses, whatever. And the problem is that Lego does a very good job modeling these. So the underside of the Lego with the little circles and the bumps and stuff, and the little tiny word Lego on the top of each circle, they model that. But you don't see very much of that here. So they use optics to trace rays at your finished model. And any polygon that never gets hit by a ray is inside your model. And so they pull that out. And so all that gets rendered is the visible whole of the model, the stuff that you can actually see. And again, that's an offline review process done on Lego's server farm. Next slide. Okay, and okay, next. And next. Okay, so the other, now we're making a big transition to stuff you can do in real time in the game. We're not baking, we're not on servers anymore. We're on the game player's machine. So the first thing you can do is not drawing pictures. It's geometric acoustics. It's rendering sound. So you've got your car driving through the city. It's making a lot of noise. You've got your cop car somewhere else. It's making a lot of noise. You want to be able to hear the siren of the cop car and know where it is. So you want the sound to bounce off the buildings and so on. So that can be done with ray tracing. Dolby is doing this, I'm not for games, but then the Gamma Research Group at UNC is doing this for games. Go to the next slide and let's see if we can get this video to play. This video has audio. Click one more time, see if that starts the video. All of this is working great on my laptop. Okay. Maybe you're just going to have to trust me how awesome this is. It's awesome. Okay, well, can you click and then do see if a bar appears to scrub through the video? Okay, nope. Okay, so no audio there, but what it was a singer in a cathedral, and first you heard just the very flat singer in a sound booth with no echoes at all. Then inside the cathedral, she's singing, and you hear all the echoes, and then the player walks through. And the echo changes as you get closer and farther away and all of that. And that can be done in real time in your game today. Now the other non-rendering use of real-time ray tracing that I'd like to talk about is using ray tracing for collision detection and line-of-sight queries. And let me guess, there's no chance of, okay, no live demo on this. I actually had a live demo for this one. This was using OpenGL to draw the pictures, and CUDA to compute where each of these 512 little guys should move each frame, and then was using optics to trace 256 green little feeler rays coming out of each actor to see what they were touching, and then 512 squared over 2 rays between each actor and each other actor to see who they can see. And then based on who you can see and what you're touching, CUDA figures out where you should move next, and then OpenGL draws it. And this is on a very tiny OpenGL, or very tiny NVIDIA GPU in a laptop, but it still was real time at several million rays per second. Okay, next slide. So that's it for in-game non-rendering. So now we'll get into actually using ray tracing to draw the shiny pictures that you all love. So, on top here we have some cars rendered with Direct3D. I can't remember what game I ripped this image from. But you can see they've got reflections off the windshield, reflections off the hood, and headlights exist. Now this is my boss's car, seriously. It has reflections off the windshield, reflections off the hood, and it has highly complex lighting within the headlights. And I just got email last week from a friend who works for, I can't remember which motorcycle manufacturer, but he was asking me if I could help him do a ray tracing simulation of his headlights on the motorcycle he's designing. Because they care not just about how it looks when you look at the headlight itself, it has to look cool, but they also care about the field of light that it projects. It has to not go into the eyes of oncoming drivers, but it has to go high on your side of the road. So they care about ray tracing in 2 ways there. And then we care about it in game. We want our headlights to look like this, not like this. Okay? And the good thing is that look what small percent of the screen is headlights. Only maybe 5%. So if we could put a box around that and just ray trace the headlight and use Direct3D for everything else, we could do that in real time, and I think we can do it today. Here on the right, another case of something where we really care about the visual quality, but we're not getting it, is eyes and eyeglasses. Okay, this is something I rendered over the weekend. Took me about 5 seconds to build the model and another 2 seconds to render it. Just kidding, this is a real guy. So the eyes say a lot, and the eyeglasses say a lot more, and they have effects like the caustics here. Now we're working with a major film studio that's using optics to do the animation. Okay, the animators have a tool where they're using optics because they care so much about the highlight on the eye. The highlight has to be ray traced, even in the pre-visualization, not even the lighting pre-visualization, the animation pre-vis. They care that much about what the eyes are doing and what the reflections on the eyes are doing. So ray tracing is the right answer for drawing pictures of eyes and eyeglasses, because that's what people focus on. So spend a few milliseconds of your per frame budget on the eyeglasses or on the headlights, and I think you'll get a difference in the visual quality that your users feel. So that's my theory. No one's done it yet. Go out and do this and let me know how it goes. Actually, I think Esteban's students have come the closest of anyone to doing this, and on Monday I'll get some demos from them, I think. Okay. Okay, someone is doing this offline. This is a company that's using optics to make car commercials for Toyota mostly. Okay, so this is rendering the headlight with Direct3D, rendering the headlight using CPU ray tracing. It took 60 minutes. Rendering the headlight using optics took 6 seconds. And the Toyota marketing manager says that he can see the difference between this and D3D, but cannot see the difference between this and this. That's what we want. Okay. Now, hopefully we'll get to some demos. Can we play this video, do you think? That would be awesome. Okay, let me talk here really briefly. To do real-time rendering in games of anything other than the static level, you've got this problem that your stuff is moving around. And do you remember the slides about this, about building the bounding value hierarchy on your geometry? That takes time. And so if all your geometry is moving every frame, you have to do that every frame. So my group is researching that problem. How can we build the bounding value hierarchy really super fast on the GPU? So we have papers on, this is one by one of my employees and me from a year ago. This has since been superseded by someone in NVIDIA research that can do it even faster on the GPU. So this is rebuilding the entire bounding value hierarchy every frame. And it takes about 8 milliseconds for a million polygons. So because that's not quite real time, we have another approach, BVH refinement. This is an idea I had about 3 years ago that was done by a student at the local university, and then he came and was my intern last summer and put this into optics. And so the approach here is to not rebuild every frame. It's just to look at what triangles move and then adjust the bounding value hierarchy, detach some of the nodes, and attach them to other parent nodes so that it can traverse faster or where the geometry has moved to. Okay, let's see the video now. So this is a demo that we made about 6 months ago. Real-time fracture of the glass, real-time dynamics of the stuff moving around, and real-time ray tracing of the light reflecting and refracting up to 12 times through this pile of broken glass. And this is it. Okay, so the hybrid ray tracing rasterization is what I was suggesting earlier with the headlights and the eyeglasses, the water and the broken glass. Those are all special effects that you would have in your screen. Not every pixel would be ray traced, just the parts that need to be ray traced. That's what I'm suggesting right here. Okay, I hope we can get this one to play. This is nothing. Okay. Can you push escape? And let's go back to let's go out of presentation mode. And okay, maybe it's not worth it. Okay, let's go back into it. Okay, so this was real-time ambient occlusion using optics in Quake 2, and it's about 3 years old. It had the guy running around, shooting everybody. The blood splatters and explosions and so on were all OpenGL, but the ambient occlusion was real-time using optics. And I'm really sorry that we can't show it to you here. Okay. Okay, so now the final thing that I'd like to talk about is ray tracing everything in the game. This is doing the global illumination with ray tracing and the rendering the geometry. Okay, and this is what path tracing gives you. So there's 3 advantages to doing this. One is it is a lot easier in the game engine to just implement path tracing than it is to try to do shadow maps and have another special effect for reflections and another special effect for caustics and deal with dynamic geometry and static geometry. All of those are separate things that usually don't play well together. You can get one of those perfect and the others just kind of don't work well. But ray tracing unifies all of that into a single, easy to understand framework. The second thing it does for you is it simplifies the art pipeline. All of the pre-baking that I showed you, you don't have to do any of that. The artist just provides the material, just says how this surface interacts with the light. The artist doesn't have to know anything about the rendering algorithms, and there is no pre-baking, which means there's a lot fewer texture maps and a lot quicker turnaround time for the artist. And then the third thing is, this is correct. This is real physics drawing the picture. So that's 3 reasons that we would want real path tracing in games. So, how close are we? Okay, these are some images that I rendered on the plane on the way over here, thinking about how many rays you have to trace per pixel. So this is 1 ray per pixel. So it just goes in and it bounces in some direction and does the ambient occlusion calculation. This is 9 rays per pixel, 18, 36, 72. This is pretty much where I'm thinking games are going to land right here. So I think, but I did my calculations with 50 paths, 50 samples per pixel. And on each of those paths, let's say they bounce on average 4 times. So there's 4 rays in a path. And that would be true for an outdoor scene. For an indoor scene, where the light's on in the next room, but it's not on where you are, the light has to bounce off the walls to get to where you are. And if it doesn't do that, you're in complete blackness. So indoors, your paths may be much longer than 4 rays. But assuming an average of 4, 50 paths per pixel, 2 megapixel display, 30 frames per second, that's 12 billion rays per second. So are we there? You would have heard about it if we were. So we're not. The GeForce GTX 680 can do about 350 million rays per second in a maybe 2 or 3 million polygon data set, which is realistic for EM level right now. So we need about a 36x speed up to get from where we are today to real-time path tracing in games on a high-end single GPU system. So we can get that 36x speed up by waiting 7 years. Moore's Law should get us there, though actually GPUs are going quite a bit faster than Moore's Law. But we could just wait and we'll get there. We could also do, like I said, there's 3 ways to optimize things. Better GPUs, better algorithms. We're still doing research on that. We have car keys and other parts of the algorithm. And better micro-optimization. And we're doing that in optics as well. And if you use optics, then you don't have to do the micro-optimization yourself. You get it from us for free. So, but we're still some years away. But let's look at path tracing for games. Let's go back one. So these next 2 are from the Brigade renderer, which is a GPU-based ray tracer by Jaakko Wicker and some others. It's being used by Otoy Corporation. This is a game they made. It's a car driving around in a city. And you can see how grainy this is. Lots of excellent film grain. Actually, this is the path tracing noise. So this is 1 ray per pixel. So Brigade can do one path per pixel per frame. And if they do that, it goes real time. And then if the camera stops moving, then it refines and it does more rays per pixel and it stops looking noisy. So here's back one. Okay, so this is also Brigade, also path tracing. You notice the noise is gone. How did they do this? They did this with a big rack full of NVIDIA GPUs, and they can do that in real time, and it looks good. So this is where we want to get to. Okay, we want this on 1 GPU in your phone. Okay, but you can get it today if you happen to have a rack full of GPUs. I suggest you try it. Okay, so this is my big finish video that's not going to work. Okay, but we can give you a still of this. If you push escape, and in the slide sorter view, find the slide that's sitting next to this one. It's hidden. Right-click on it, go down to the bottom of the menu where it says Hide Slide, and uncheck that. Oh, okay. This is the other half of the big finish. Okay, so this is by my group. It's a GeForce demo that we made called Design Garage. This is real-time. This is interactive path tracing of real models. So this is a Bugatti Veyron. This is the interior of a Bugatti Veyron. You can see the soft shadows. You can see down here. It's only indirect illumination that's hitting this. You only get this with path tracing. You get some interreflections between non-convex parts of the car. So right in here, we're seeing reflection off of this, and then off of this, and then off of the ground, for example. So this is path tracing. And again, on a Fermi GPU, our old architecture, this took about 10 seconds to resolve. On a Kepler GPU, even faster. And then in the future, even faster. So I had a video of interacting with these models, but you don't get to see that. You know what? If anyone wants to grab me afterwards, I'll just sit right there on the stairs with my laptop, which has an NVIDIA GPU and it works, and we can all watch the videos together, okay? Let's see, go to the next slide. Okay, so this is the end. So hopefully I've answered the question, or at least I've given my opinion of when would you want ray tracing in games and why. And you want it when you're doing offline light making, and when you get that, you get it today. Lots of companies are using it. If you want in-game special effects, the collision detection, line of sight queries, audio propagation, eyeglasses, and so on, you can get that tomorrow. Just go implement it, and it'll be there. And then if you want the real-time path tracing, it's coming. There's no way that it's not coming. It'll be here in 7 years if we're lazy, sooner if NVIDIA does a good job. And that's the end. Thank you all very much.
Thank you, David. Nice speaking. Só para esclarecer, o notebook dele não sintonizou com os projetores. Por isso que foi o problema dos vídeos não rodarem. A gente não estava conseguindo a saída de vídeo dele, do notebook dele. So I think we have a few minutes for questions. Someone wants there.
First question.
Okay, thank you for the talk, first of all. And after that, I was wondering, I'd like to know how much of the work you develop in optics is about research and is about development. What percentage would you divide these two topics? Additionally, how much of the research that is being done in universities and academy do you use at NVIDIA, and how much do you have to create to be able to develop these topics?
Okay, for your first question, within the optics group, which is about 10 people, it's about 80% development and customer support, some of which is a little bit researchy, and then about 20% pure research. But also within NVIDIA, we have lots of other people doing ray tracing research. People in Finland, Russia, Germany. Oh, and then I forgot to mention, we have, you've heard of Mental Ray. NVIDIA owns Mental Ray, and we have about 60 ray tracing experts, mostly in Berlin, doing ray tracing research and development there. And let's see if I can succeed in going back one slide. That red shiny character, that was by the researchers in our Berlin office. One more forward. That guy. This is a new renderer that mostly our Berlin office has made that uses optics, and this is an interactive ray tracer for design visualization. So